Hello, welcome. My name is John Morrow. I am a professor of materials science and engineering at Penn State University. Welcome to my video on the first law of thermodynamics, a modern interpretation. This is work that I did together with my dear friend and colleague, Professor Long-Ching Chen, who is the Hammer Professor of Materials Science and Engineering at Penn State and author of the textbook Thermodynamic Equilibrium and Stability of Materials. This modern statement of the first law is the form of the first law of thermodynamics adopted in this textbook. It is also something that we elaborate on even further in this article shown at the top, a modern statement of the first law of thermodynamics, which is published in MRS Bulletin, the Materials Research Society Bulletin. So what I'd like to do with this video is to explain the rationale for why we are revisiting the first law of thermodynamics, introduce this modern statement of the first law, and give a few examples of applying this to some simple systems. If you would like to learn more and dive in deeper, we have more complicated examples in this MRS Bulletin paper. But let's dive in. Anytime we are studying thermodynamics, there is some system that is of interest for us to study. This system has an internal energy associated with it, which is given by this capital letter U. So U is our internal energy of this system that we are studying. This system is contained within or somehow coupled to the surroundings. The surroundings have an internal energy that is associated with them, and that is labeled as U sub ser for the internal energy of the surroundings. So the system is contained within or coupled to the surroundings. And if you take the system and the surroundings as a whole, together they make up the universe. So we have the system that we want to study. The surroundings is everything else. And if you put them together, that gives us the entire universe. And the internal energy of the universe, therefore, is this total internal energy, and that is simply equal to the summation of the internal energies of the system and that of the surroundings. So the internal energy of the universe, U total, is equal to the internal energy of the system, U, plus the internal energy of the surroundings. Now, the first law, at its most fundamental level, is a statement of the conservation of energy of the universe. The first law of thermodynamics, in other words, states that the energy of the universe is a constant. Energy can neither be created nor destroyed. It can merely be converted between different forms or transferred between the system and the surroundings. But regardless of the flow of energy or the transfer between different types of energies, if you add up the total internal energy of the universe, that must remain constant. The assumption here is that the universe is isolated. And what this means is that the internal energy of this universe, U total, is equal to the summation of the internal energy of the system with that of the surroundings, and this total summation here is constant. So if we consider the internal energy from the point of view of the system or the surroundings, there can be transfer of internal energy between the two, but it is a zero-sum game, meaning that the total amount of energy always has to remain constant. Now, if we go back in time, historically, the first law of thermodynamics was written originally by Clausius, as shown here, where this delta U is the change in the internal energy of the system. So we're looking at the first law from the perspective of the system under studied, and there is some change of the internal energy of that system, which is given by delta U. And this historical statement of the first law has two contributions to it. First is the heat transfer into the system, and that is designated by a capital Q. And then the work being performed by the system, which is a minus W. So the change in the internal energy of the system has this heat transfer contribution Q minus this work that's being performed by the system. Now, this statement of the first law I think is especially interesting from an engineering point of view. For example, if you are a mechanical engineer and want to study how much work can be performed by a system, it's very natural to write it in this way. That being said, there are some limitations to this traditional form of the first law. Firstly, the way that this is written here, it is just written for a closed system, so this does not allow for the transfer of chemical matter between the system and the surrounding. Um, Secondly, if you include this transfer of chemical matter, that transfer of chemical matter brings along a change of internal energy. It brings along a change of volume to the system as well, and that may be difficult to incorporate into this formulation of the first law expressed as heat and work. The other complication is some confusion around the sign of the work. And I remember as a student, I was confused by this because sometimes I would see the first law stated as Q minus W. Other times I would see it expressed as Q plus W. So traditionally, Q minus W is used because the work is performed by the system. And many of the more modern textbooks, this is expressed as Q plus W, where now this is the work being performed on the system rather than the work being performed by the system. And so it's not always clear what is being meant when this term work is used, and this can be a point of confusion for students. And so our modern approach to the first law avoids even needing to define work in the first place, and so it bypasses this potential point of confusion. And this modern statement of the first law that we're going to introduce goes back to some more of the fundamental quantities that are being exchanged between the system and the surrounding. So without any further ado, let's revisit our first law of thermodynamics, considering the starting point here that the total internal energy of the universe is equal to a constant. If we take the differential operator on that, so if we consider d u total, this must be equal to zero because any change of a constant must be equal to zero. And so what this means is that the du, this infinitesimal change of the internal energy of the system, plus the infinitesimal change of the internal energy of the surroundings, that must be equal to zero. Or equivalently, if we express this in terms of finite changes, the delta U of the system plus the delta U of the surroundings is equal to zero. So this means that the delta U of the system must be equal to the minus delta U of the surroundings in order to maintain conservation of the total internal energy of the universe. Now, what we want to do is consider the three fundamental contributions to the internal energy of the system. So going back to Gibbs' formulation of thermodynamics, we consider three contributions to the internal energy of the system U. There is the thermal energy contribution, which is U sub T, the mechanical energy contribution, which is U sub M, and the chemical energy contribution, which is U sub C. So three different types of internal energy here: thermal, mechanical, and chemical. And if you add them together, you get the total internal energy of the system. Now, for a simple system, there are three basic variables that represent three types of matter corresponding to these three different types of energy. The first is thermal matter, better known as entropy or S. Thermal matter is the carrier of the thermal energy. So entropy can be considered as a thermal matter that carries thermal energy. Mechanically, the corresponding mechanical matter is volume, V. So volume as mechanical matter is a carrier of the mechanical energy. And then finally, we have chemical matter, which is N, the number of moles of our chemical species. So three different types of energies: thermal energy, mechanical energy, and chemical energy, and they are carried by their three different corresponding types of matter: the thermal matter, which is entropy, the mechanical matter, which is volume, and the chemical matter, which is the number of moles, N. Now, if we take the ratio of any of these types of energy to its corresponding types of matter, we get what is called a thermodynamic potential. This thermodynamic potential is an intensive quantity because it is the ratio of two extensive quantities. So energy and matter are both extensive quantities, so if they both increase proportionally with the size of the system. If you increase the size of the system, for example, the amount of thermal energy will go up, the amount of thermal matter will go up proportionally. But if you take the quotient of the two, so take the energy divided by the matter, you're taking two extensive quantities, dividing them together, and then you get an intensive quantity, which is the potential. So a thermodynamic potential is any type of energy divided by its corresponding amount of matter. So for example, the thermal potential is the amount of thermal energy, U sub T, divided by the amount of thermal matter, entropy. And if you take this amount of thermal energy divided by the amount of thermal matter, what you get is the thermal potential, which is better known as the temperature, T. So temperature is an intensive quantity, but thermal energy and entropy are both extensive quantities. If we consider the mechanical potential is just the mechanical energy divided by the mechanical matter. So the mechanical energy is U sub m divided by the amount of mechanical matter, which is the volume. And the ratio of those two gives us the mechanical potential, which is simply the negative pressure. The reason for the minus sign here is just based on the conventional definition of pressure, which is based on a hydrostatic compression rather than hydrostatic tension. And because of that, this picks up a minus sign here. So the mechanical potential is negative pressure. Now, the third type of potential, corresponding to our third type of energy, is the chemical potential. The chemical potential is simply the ratio between the chemical energy and the amount of chemical matter. So this is the U sub C divided by N, the chemical energy divided by the chemical matter. And this is what gives us the chemical potential, which is labeled with the Greek letter mu. So we've got three different types of potentials here: temperature, pressure, and chemical potential. And what we want to do now is express the total internal energy of the system in terms of those potentials multiplied by their corresponding amounts of matter. So taking our equation from the previous slide for the total internal energy of the system, U, this total internal energy of the system, is equal to the summation of the thermal, mechanical, and chemical contributions to the internal energy. Now, how can we express this amount of thermal energy here, UT? If we go back up to this top equation, you'll see that UT is equal to our thermal potential multiplied by our amount of thermal matter. So our UT is equal to T times S. So this T, the temperature, multiplied by the entropy, gives us the amount of thermal energy. So our contribution of our thermal contribution to the internal energy of the system is simply the thermal potential, the temperature, multiplied by the amount of thermal matter, which is the entropy. So T times S. Likewise, for our mechanical energy here, U sub m, if we go back up to the second equation, you can see that U sub m is equal to minus the pressure times the volume. So it's equal to our mechanical potential, which is the negative pressure, times the amount of mechanical matter, which is the volume. So we can replace this U sub m in our equation with minus P times V. This gives us our mechanical contribution to the internal energy. Finally, we need our chemical contribution to the internal energy, U sub C. Likewise, we go to this third equation here and see that the U sub C, our chemical energy is equal to our chemical potential mu times our amount of chemical matter n, the number of moles. And so we replace this U sub c by mu times n, the chemical potential times the amount of chemical matter. And so now we have an equivalent expression for the internal energy of the system U, which is equal to Ts, that gives the amount of thermal energy, minus PV, which gives the amount of mechanical energy, plus mu n, which gives the amount of chemical energy. Now, what we want to do is consider the first law in terms of an exchange of these three different types of matter. We can have an exchange of thermal matter, which means an exchange of entropy. We can have an exchange of mechanical matter, which means an exchange of volume. Or we can have an exchange of chemical matter, which means an exchange of the number of moles of a given species. So here we have a diagram that shows the system on the left, and this is coupled to the surroundings here on the right. The system has its set of three potentials here defined. The thermal potential, which is the temperature, the mechanical potential, which is the pressure, and the chemical potentials for each type of species, each type of chemical species. Likewise, the surroundings has its temperature, pressure, and set of chemical potentials. But the exchange here, the exchange is an exchange of matter. And so there can be an exchange of entropy, where this dSE is the entropy entering the system. You could also do this from the perspective of the surroundings and have this dS which is the entropy entering the surroundings. Then we have an exchange of mechanical matter. The exchange of mechanical matter is a volume exchange between the system and the surroundings, so this dV. Finally, we can have an exchange of chemical matter. The exchange of chemical matter is a change of the number of moles of each of our chemical species, so this dNi. Now what we can do is express our change of the internal energy of the system or the change in internal energy of the surroundings in terms of our equation from the previous slide, which means each of these three different types of potentials, the temperature, the negative pressure, or the chemical potential, multiplied by the change in that corresponding amount of matter. So for the thermal contribution to the change of internal energy, we have the thermal potential, which is the temperature, multiplied by the change in the amount of thermal matter, which is ds. That product gives us the change in internal energy associated with the thermal processes, minus our PdV. This is our mechanical contribution, which is our mechanical potential, the negative pressure, times our flow of the mechanical matter, which is the change of volume. So this middle term gives us the mechanical contribution. And then the third term here gives us the chemical contribution. This is just the chemical potential multiplied by the amount of chemical species entering the system here, d sub n. So these three terms give us the thermal contribution, the mechanical contribution, and the chemical contributions to the change of the internal energy of the system. And those are all expressed in terms of something that's very natural and very fundamental to our thermodynamic problem, which is the exchange of these three different types of matter, the exchange of thermal matter, the exchange of mechanical matter, and the exchange of chemical matter. And to convert those exchanges of matters to energies, they are multiplied by their corresponding potentials. So this equation here on the lower left is a statement. This is our modern statement of the first law of thermodynamics from the perspective of the system. Now, if you see on the right-hand side, there is an equivalent expression here with all the same terms, but now just expressed in terms of the surroundings. So expressed in terms of our potentials for the surroundings, the temperature of the surroundings, the pressure of the surroundings, the chemical potential of the surroundings, multiplied by the amount of each type of matter, thermal matter, mechanical matter, chemical matter, entering the surroundings. And this gives us an equivalent expression of the first law, but now from the perspective of the surroundings. These two equations are the same. They have the same form. It's just one is from the perspective of the system, and the other is from the perspective of the surroundings. In a future video and in a future article together with Professor Chen, we're going to take a deeper dive into the nature of the surroundings itself, how the surroundings are defined, and basically show that it's completely arbitrary about what you define as the system versus what you define as the surroundings. They are basically interchangeable. And conventionally, what we do is we choose whatever it is that we're interested in studying, that becomes the system, and then everything else becomes the surrounding. So just keep in mind the choice of system versus surrounding is somewhat arbitrary. But for the remainder of the video, I'm going to be taking the perspective of the system here, as is conventional when discussing the first law. So this modern statement of the first law of thermodynamics then is du, the change of internal energy of the system, is equal to three different contributions: the change of the thermal energy, the change of the mechanical energy, and the change of the chemical energy. And this expression builds upon fundamental thermodynamic quantities because it builds upon our three different potentials: the thermal potential, the mechanical potential, the chemical potential. And then each of those is multiplied by the exchange of their corresponding amounts of matter. So the exchange of thermal matter, this change of entropy, the exchange of mechanical matter, which is a volume exchange, and then the exchange of chemical matter, which is an exchange of the number of moles of different species. So this is a much more natural expression of the first law of thermodynamics compared to the previous expression in terms of heat and work. It also completely avoids defining those quantities and avoids all the confusion associated with the sign of the work and whether the work is being performed by the system or on the system. It also is a much more natural way to apply the first law of thermodynamics to open systems, because you can see that the exchange of matter here is treated just like the exchange of a thermal matter or mechanical matter. So the exchange of chemical matter for open systems is treated naturally just the same way as the exchange of the two other types of matter. It also applies equally well to reversible and irreversible processes. What I'd like to do is show you a few examples of how this can be applied. These are just some simple examples. If you wanted to go into more detail or see some of the more complex examples, please check out our paper in MRS Bulletin. Let's consider application to a closed system, first of all, because this will actually show us how this connects back to the traditional statement of the first law. For a closed system, we have the exchange of two different types of matter. There can be an exchange of thermal matter here, with entropy entering the system. There can be an exchange of mechanical matter with volume entering the system. But if the system is closed, that means that there is some sort of impermeable boundary between the system and the surrounding, which prevents the flow of chemical matter. And as a result, this dN, this exchange of chemical matter here, is zero, and therefore there are just two remaining terms in our change of internal energy of the system, the thermal term here and the mechanical term. And it may become apparent then that the connection to that traditional statement of the first law for a closed system is that our change of internal energy here has these two contributions: the exchange of thermal matter. Conventionally, this would be expressed as the flow of heat, dq, and then an exchange of mechanical matter here, which corresponds to this dw, the work that is being performed on the system. So this is how this modern statement of the first law can connect back to the traditional statement. But if you have an open system, you can see how natural it is then to include the chemical exchange as well. Let's consider a few other really simple cases. Next up is application to isolated systems. Isolated systems are the most simple of all because with an isolated system, there is no exchange of thermal matter, so there's no entropy entering the system. There is no exchange of mechanical matter, so the dV is also zero, and there's no exchange of chemical matter. So all three of these terms are zero from the point of view of an isolated system, which means that the total change of the internal energy of an isolated system is equal to zero. Du is equal to zero. This is the first law of thermodynamics for an isolated system, and this should come as no surprise because the universe as a whole is isolated, and that means that energy is conserved for not just the universe, but for any isolated system. So du equals zero for an isolated system. Now, what if we allow for the exchange of thermal matter? Let us consider a constant volume process for a system. So for this constant volume process for a closed system, now we've got no change in volume because the dV is equal to zero. We also have no change of the chemical matter because it's a closed system. And in this case, we're left with just one term, which is the thermal term. And so we have some amount of thermal matter here that is being exchanged between the system and the surroundings. That amount of thermal matter entering the system is expressed as ds. And if we multiply that by the thermal potential, the temperature, that gives us then the total change of the internal energy of the system. It only has this contribution from the exchange of thermal matter. And if we connect that back to the conventional description of the first law, this corresponds to dq. This corresponds to the heat flow between the system and the surroundings. And therefore, if we express this in terms of a finite change of the internal energy, the delta U is just equal to Q, the heat flow in that case. Now, what if we make this slightly more complicated and now we allow for the exchange of both thermal matter and the exchange of chemical matter? This would be a constant pressure process rather than a constant volume process. And we'll keep this as a closed system where the dN is still equal to zero. Now we have two contributions here. And so the change of internal energy of the system has this thermal contribution due to the product of the amount of thermal matter entering the system, the ds, multiplied by its thermal potential T. And then the mechanical contribution is the amount of volume entering the system multiplied by the mechanical potential, which is the negative pressure. So add those up. That gets you the total change of the internal energy of the system. Now, if we bring this mechanical part, this minus P dV, over to the left-hand side of the equation, that becomes a plus P dV. And then all that's left on the right-hand side is our thermal contribution, or TdS. This thermal contribution is the exchange of heat, the dQ. Now, if we assume that that there's no net change of volume between the system and the surroundings, in other words, the only change of volume in the system is equal to minus the change of volume of the surroundings, then we can rewrite this left-hand side of the equation as d of, so change in internal energy plus pressure times volume. And you might recognize this, the internal energy plus pressure times volume. That is the definition of enthalpy. And so in this case, we can write the change of enthalpy, the dH, H's enthalpy, is equal to the dQ. So for an isobaric system, so a constant pressure case, the heat flow here can be expressed in terms of the change of enthalpy. So delta H in this case is equal to Q. So these are just a few simple cases. But to summarize here, this modern statement of the first law of thermodynamics is expressing the change of the internal energy of the system in terms of the changes of the three corresponding contributions to the thermal energy, the change of thermal, the change of mechanical, and the change of chemical energies. For each one of those, for the thermal, mechanical, and the chemical contributions, we express them as their corresponding potentials multiplied by the amount of change in that corresponding amount of matter. So the change of the thermal energy is the thermal potential, the temperature, times the change of the thermal matter, the ds. Same thing for the mechanical contribution. It's the mechanical potential minus the pressure times the change of the mechanical matter, which is the change of volume. And in the chemical case, it's the chemical potential times the amount of change in the chemical matter. So this is a much more natural description of the first law because it goes back to these fundamental thermodynamic quantities. It focuses on the exchange of these three different types of matter between the system and the surroundings. It is much easier to extend this to open systems. It's easy to apply this to either reversible or irreversible processes. And it avoids defining unnecessary quantities like the Q, the heat, or the work W, although you can connect it back to that conventional description of the first law if you wish. It also avoids the confusion that is often associated with the sign of the work, whether the work is being performed by the system or on the system. So this is just a simple introduction to this modern statement of the first law. We go through a lot more detailed examples of this, including some more complicated examples where maybe there's a temperature difference between the system and the surroundings, or a pressure difference between the system and the surroundings, or what if you have internal irreversible processes taking place. All of these more complicated cases are dealt with in our paper here, published in MRS Bulletin. So please check that out if you want to go into those more complicated cases. And of course, if you want a more comprehensive coverage of thermodynamics in general, check out Dr. Chen's textbook. So thank you all for joining me for this discussion of the first law. If you enjoyed the video, please be sure to give it a like and subscribe to the channel. Thank you very much, everyone, and I'll see you next time.